In 2013, a team of astronomers working at Eötvös Loránd University in Budapest published a paper that received surprisingly little mainstream attention for something that quietly invalidated a foundational assumption of modern cosmology. The paper described a ring, or more precisely, a statistically anomalous clustering of gamma-ray bursts distributed across a region of sky that, when translated into physical dimensions using their measured distances from Earth, spanned approximately 9.7 billion light-years from one edge to the other. That number is not a typo, it is not a misprint, it is a measurement, and it is nearly 6 times larger than the theoretical maximum size that any coherent structure in the universe is permitted to reach, according to every cosmological model built over the preceding century. The structure they found was named the Hercules Borealis Great Wall. It sits in a part of the sky bracketed by the constellations Hercules and Corona Borealis at a redshift of between 1.6 and 2.1. Redshift, as we will explain in detail shortly, is the language in which the expanding universe writes distance. A redshift of 1.6 to 2.1 means the light we use to detect its constituent events left those locations when the universe was somewhere between 3.2 and 3.8 billion years old, when the cosmos had not yet reached 1/3 of its current age, when the Milky Way was still assembling itself from colliding protogalactic clouds, and when the region of space that would eventually become the solar system had not yet begun to collect its disk of gas and dust. Whatever happened out there in that enormous volume of ancient space to create an overdensity of explosive stellar deaths so large it apparently breaks the rules cosmologists have written for the maximum permissible size of any structure, that is the central question this video will pursue. The question is not merely astronomical, it touches the foundations of how we model the universe, the mathematical scaffolding that underlies every cosmological prediction, every interpretation of the cosmic microwave background, every calculation about dark energy, dark matter, and the long-term fate of the cosmos. If the Hercules Borealis Great Wall is what the data suggests it is, something in that scaffolding is incorrect. And if something in that scaffolding is incorrect, we need to find out what, because the implications propagate outward in every direction. If you are ready, join us as we follow this structure from its detection through its deepest implications and all the way to the edge of what human science can currently say about it. Let us begin. There is a principle that underlies virtually every model of the universe that has been constructed since Albert Einstein first applied the field equations of general relativity to the cosmos as a whole in 1917. It is called the Cosmological Principle, and it states, in essence, that the universe is homogeneous and isotropic. Homogeneous means it has the same properties at every location. No point in the universe is fundamentally different from any other. Isotropic means it looks the same in every direction. There are no preferred axes, no cosmic north or south. This is not a philosophical preference or an aesthetic desire for neatness. It is a mathematical convenience with enormous physical consequences. When you assume homogeneity and isotropy, the field equations of general relativity, which in their full generality describe the curvature of spacetime at every point as a function of the energy and momentum content at that point in a system of 10 coupled non-linear partial differential equations, simplify into a pair of equations that can be solved analytically and used to make predictions testable with telescopes. These are the Friedmann equations, and they form the backbone of all modern cosmology. The cosmological principle is, in a real sense, what makes modern cosmology possible as a quantitative science rather than a philosophical exercise. But it is worth pausing on what this principle actually claims, because people often misunderstand it. It does not say that the universe looks the same everywhere right now at the scale you can see with your eyes or even with a large telescope. Obviously, it does not. Galaxies cluster together. There are vast, empty voids between them, some stretching for hundreds of millions of light years. There are filaments, long, thin threads of galaxies tracing paths through the cosmic web. There are sheets and walls of galaxies compressed by the large-scale flows of matter in the expanding universe. At the scales of galaxies and galaxy clusters, the universe is wildly irregular, textured, lumpy. What the cosmological principle claims is that if you average over a large enough volume, if you zoom out far enough, those irregularities cancel out. The lumps balance the voids. The density in one region matches the density in another. And the scale at which this smoothing out should occur has been calculated with considerable precision from the physics of structure formation, approximately 1.7 billion light-years. Beyond that threshold, the theory says the universe should be statistically uniform. Density should not vary meaningfully from one 1.7 billion light-year cube of space to the next. Structures should not exist. The cosmos should look like a featureless fog. Think of it this way. Imagine you're standing inside a tropical rainforest in Nigeria. Looking in any direction, you see a tangle of trees, vines, leaves, and shadows. The distribution of biomass around you is wildly non-uniform. Thick trunk here, open clearing there, dense canopy above, bare root system below. But if you rise in a helicopter and look down at the same forest from an altitude of 10 kilometers, it resolves into a texture, green and roughly uniform across the landscape, with some variation in shade and density, but nothing that looks like a coherent large-scale structure. The cosmological principle is the claim that the universe has such an altitude, that from high enough above, the lumps dissolve into a uniform haze. And that altitude, in cosmological terms, corresponds to a physical scale of roughly 1.7 billion light-years. Below that scale, structure is expected and observed. Above it, the theory says, structure should not exist. The Hercules Borealis Great Wall at 9.7 billion light-years is not 1.8 billion light-years or 2 billion light-years, a marginal violation of the limit. It is nearly 6 times the theoretical maximum. This is not a measurement that is slightly in tension with theoretical predictions. It is a measurement, if accurate, lives in a regime the theory doesn't know how to explain. And to understand why this matters more deeply than a simple record-breaking announcement, we need to understand where the theoretical limit comes from, because it doesn't come from a preference or a convention. It comes from the physics of causality itself. It comes from the speed of light and the age of the universe, and those are not things you can negotiate. The speed of light is approximately 299,792 kilometers per second. In 13.8 billion years, the current age of the universe, light has had time to travel a certain maximum distance from any given point. That distance, accounting for the expansion of space over that time, defines the particle horizon, the maximum radius from which any observer can have received information since the Big Bang. Two regions of space can only share a coherent physical structure, can only have their matter distributions causally correlated, if they were at some point within each other's particle horizons. If two regions were never in causal contact, gravity could never have organized their matter into a shared structure. The particle horizon at the epoch of cosmic history, corresponding to the Hercules Borealis Great Wall, was considerably smaller than the structure's claimed extent. What this means is that under standard physics and standard initial conditions, the regions at opposite ends of the structure were never in causal contact at the time when the structure would have had to begin forming. They did not know about each other, and yet, somehow, they are apparently organized into a coherent overdensity. Something about that sentence needs to break. Either the structure is not as coherent as the data suggests, or the physics is not as settled as we think. Before we can fully appreciate what a 9.7 billion light-year structure represents, we need to build a ladder of scale deliberately and carefully, rung by rung, because human intuition was not designed for cosmological distances. The nervous system that allows you to catch a thrown object, navigate a crowded room, or judge the distance to the horizon evolved to operate in a world of meters and kilometers. It has no native sense of what a light year means, let alone a billion of them. So we are going to build that sense from scratch, starting where you are right now. Start with your own hand. Held in front of your face, your hand is perhaps 20 centimeters across, 0.0002 kilometers. The atoms in your skin are separated from each other by distances on the order of a few angstroms. 1 angstrom is 10 billionths of a meter, or 0.000000000001 meters. The nucleus of a single atom is roughly 100,000 times smaller than the atom itself. If you could scale a hydrogen atom up to the size of a football stadium, 100 meters in diameter, its proton would be a grain of sand, perhaps 1 millimeter across, sitting at the center of the field. The rest of the atom is empty. The universe is built from emptiness, with tiny nodes of structure, and this is true from the smallest scale we can probe up to the largest. At human scale, a kilometer is about the distance you walk in 12 minutes. The city of Lagos, one of the most densely populated urban areas on Earth, covers approximately 1,171 square kilometers of land area. The diameter of the Earth is 12,742 kilometers. The distance from the surface to the center is 6,371 kilometers, about 6.4 times the length of Nigeria from north to south. If you could drill a tunnel through the Earth and fall in, ignoring air resistance and the inconvenience of the molten mantle, you would reach the other side in approximately 42 minutes, accelerating for half the journey and decelerating for the other half. The Moon sits 384,400 kilometers away, about 30 Earth diameters. If you drove there at highway speed, 100 kilometers per hour, without stopping for fuel, food, or rest, the journey would take approximately 160 days. Light covers it in about 1.28 seconds. The distance to the Moon is the baseline against which all farther astronomical distances were first measured. The Moon is close enough that radar pulses sent from Earth bounce off its surface and return in under 3 seconds, allowing its distance to be measured with extraordinary precision. But it is already so far from Earth that no human has visited it since 1972, more than half a century ago. And the Moon is, in cosmological terms, right next door. The Sun is 149.6 million kilometers from Earth, about 390 times the Earth-Moon distance. Light takes 8 minutes and 20 seconds to complete that crossing. When you look at the Sun, and you should never do so without proper protection, you are seeing it as it was more than 8 minutes in the past. The Sun is so large that you could fit approximately 1.3 million Earths inside its volume. Its surface temperature is approximately 5,500 degrees Celsius. Its core temperature is approximately 15 million degrees Celsius, where hydrogen nuclei fuse into helium, releasing the energy that has powered the Sun for the last 4.6 billion years and will continue to do so for approximately another 5 billion years. The nearest star system to our own is Alpha Centauri, at a distance of 4.24 light-years, approximately 40.1 trillion kilometers. That is a 4 followed by 13 zeros in kilometer units. Voyager 1, the fastest human-made object ever launched into interstellar space, travels at roughly 17 kilometers per second, or about 61,000 kilometers per hour. At that speed, the journey to Alpha Centauri would take approximately 73,000 years. The light from Alpha Centauri that reaches your eyes tonight left that star system roughly 4.24 years ago. It has been traveling at 299,792 kilometers per second for 4 years and 3 months before arriving at your retina. You are not seeing Alpha Centauri as it is, you are seeing it as it was. This is a critically important point that we will return to repeatedly. Every observation in astronomy is an observation of the past. The further away an object is, the further into the past we are looking. Light is fast. It is the fastest thing in the universe, but the universe is so large that even at light speed, the crossing times are immense. Looking outward in space is the same as looking backward in time. This fact, which seems like a mere curiosity at the scale of nearby stars, becomes the central operational principle of all extragalactic astronomy, and it is what makes the study of the Hercules Corona Borealis Great Wall possible. We are not seeing that structure as it is today, but as it was roughly 10 billion years ago. The center of our galaxy, the Milky Way, sits about 26,000 light-years away. The light reaching us from the galactic center right now left that region approximately 26,000 years ago, during the last ice age on Earth. The Milky Way itself is a spiral galaxy, roughly 100,000 light-years in diameter, possibly 200,000 light-years if you include the outer stellar halo, with a mass of approximately 1 to 1.5 trillion solar masses, including the dark matter halo. The central region of the Milky Way hosts a supermassive black hole called Sagittarius A star, with a mass of approximately 4 million solar masses. We know it's there because we can track the orbits of individual stars near the galactic center over many years and derive the mass of the invisible object they are orbiting. Those orbits are consistent with a point mass of 4 million suns compressed into a volume smaller than our solar system. The Milky Way is part of the Local Group, a gravitationally bound collection of approximately 80 galaxies spanning about 10 million light-years. The two dominant members are the Milky Way and the Andromeda Galaxy, also known as M31. Andromeda sits 2.537 million light-years away. The light reaching your eyes from Andromeda tonight left that galaxy when Homo habilis, one of the earliest members of our genus, was first learning to knap stone tools on the savannas of East Africa. You are looking into a past that predates our own species by 500,000 years, and you are doing it with your naked eyes. Andromeda is the most distant object visible without optical aid from a dark site. Beyond the Local Group, the nearest large cluster of galaxies is the Virgo cluster, approximately 53 million light-years away, and containing more than 1,300 galaxies bound by mutual gravity. The Virgo cluster is the gravitational anchor of the Virgo supercluster, also called Laniakea, which encompasses our Local Group along with dozens of other galaxy groups, and spans roughly 520 million light-years. Laniakea is itself just one supercluster among hundreds in the observable universe, interconnected by the filaments of the cosmic web. The Sloan Great Wall, discovered in 2003 from data collected by the Sloan Digital Sky Survey, stretches for approximately 1.37 billion light-years. When it was announced, it was the largest known structure in the observable universe, and its discovery raised early concerns about whether the cosmological principle held at that scale. Note that 1.37 billion light-years is already near the 1.7 billion light-year homogeneity limit. The Sloan Great Wall was not a comfortable confirmation of theoretical predictions. It was a yellow flag. The Hercules Corona Borealis Great Wall at 9.7 billion light-years is not a yellow flag, it is a red one, large enough to cover most of the observable sky from a certain vantage point. 9.7 billion light-years. The observable universe, the entire sphere of space from which light has had enough time to reach us since the Big Bang, spans approximately 93 billion light-years in diameter. The feature claimed by Balazs and colleagues spans more than 10% of that diameter in a single linear dimension. If you placed the Hercules Borealis Great Wall next to the observable universe, the way you might hold a ruler next to a doorframe, the ruler would be more than 10 centimeters if the doorframe were 1 meter. It is not a feature at the edge of what we can see, it is a feature that dominates a significant fraction of what we can see. And the fact that something so large, something that should be averaging out into uniformity by every cosmological rule we know, instead shows up as a coherent overdensity is what makes it so remarkable. The Hercules Borealis Great Wall was not found by pointing a telescope at a patch of sky and seeing it as a visible feature. At cosmological distances of 9 to 10 billion light-years, the individual galaxies that comprise any large-scale structure are too faint to image in large numbers with any current telescope, and even if they could be imaged, measuring redshifts for millions of such faint galaxies to map their three-dimensional positions would require an observational campaign lasting centuries. The structure was instead identified using a very specific class of astrophysical event, the gamma-ray burst, as a tracer of the underlying matter distribution. Understanding why gamma-ray bursts are ideally suited for this purpose requires understanding what they are and what makes them uniquely observable across cosmological distances. Gamma-ray bursts are the most energetic electromagnetic events known to occur in the universe. In a time window that may be as short as a fraction of a second or as long as several minutes, a single gamma-ray burst can release more energy in electromagnetic radiation than the Sun will emit across its entire 10 billion-year main sequence lifetime. They were first detected in the late 1960s by the Vela satellites, a series of spacecraft deployed by the United States to monitor compliance with the Nuclear Test Ban Treaty, looking for the gamma-ray signatures of clandestine nuclear explosions. The early Vela detections were not nuclear tests. They were something else entirely, arriving from all directions of the sky with no obvious pattern. The classified discovery was eventually published in 1973 by Ray Klubsadel, Ian Strong, and Roy Olson in the Astrophysical Journal, opening a new field of study that would take another 25 years to fundamentally explain. The key breakthrough came in the mid-1990s. For decades after their discovery, a central controversy persisted. Were gamma-ray bursts occurring within our own galaxy, or were they extragalactic, occurring at cosmological distances? The two possibilities carried radically different implications for the energies involved. If gamma-ray bursts were galactic, they needed to release a large but not unprecedented amount of energy. If they were extragalactic, the energies required were extraordinary, billions of times the Sun's total luminosity, concentrated in seconds. The Compton Gamma Ray Observatory, launched in 1991, accumulated a large enough sample of bursts to establish conclusively that their distribution was isotropic, uniform across the sky, with no preference for the galactic plane. This strongly suggested an extragalactic origin. The Italian-Dutch satellite Beppo-Sax, launched in 1996, was the instrument that settled the matter. It was capable of localizing burst afterglows to arc-second precision quickly enough for ground-based telescopes to obtain spectra while the afterglow was still bright. The first redshift measured for a gamma-ray burst afterglow in 1997 was Z equals 0.835, extragalactic, conclusively and undeniably. Today, gamma-ray bursts are understood to arise from two physically distinct progenitor systems. Long gamma-ray bursts, operationally defined as those with durations greater than 2 seconds, are associated with the core collapse of very massive stars, specifically the class of rare, rapidly rotating stars that produce a jet-forming engine upon collapse rather than a spherically symmetric supernova. When such a star exhausts the nuclear fuel in its core, the core collapses in milliseconds into a neutron star or a stellar mass black hole, and the gravitational and rotational energy released in that collapse drives two opposing highly collimated jets of plasma and radiation along the star's rotation axis at Lorentz factors, the relativistic measure of how close to the speed of light something is traveling, of between 100 and 1,000. If one of those jets is pointed within a few degrees of Earth, we detect the burst. Short gamma-ray bursts, with durations less than 2 seconds, arise from the merger of two compact objects, typically two neutron stars or a stellar mass black hole in a binary system that has lost orbital energy over billions of years through the emission of gravitational waves, and finally spirals to merger. The 2017 event GW170817, detected simultaneously in gravitational waves by the LIGO and Virgo detectors and in a short gamma-ray burst by the Fermi and Integral satellites, provided direct confirmation of this picture, one of the most significant multi-messenger astronomy events in history. Both varieties of gamma-ray burst share the property that makes them ideal for large-scale structure studies. Their afterglows can be detected and spectrally analyzed at the full reach of the observable universe. The most distant gamma-ray burst ever measured, GRB 090423, had a redshift of Z equals 8.2, meaning its light left its host galaxy approximately 13.1 billion years ago, when the universe was only about 630 million years old, and the first stars were beginning to ionize the intergalactic medium. At such distances, an ordinary galaxy would be far too faint to observe with current telescopes, but the gamma-ray burst afterglow, a rapidly fading but initially brilliant source, can be detected by SWIFT and followed up with ground-based spectroscopy to yield a precise redshift within hours of the burst. This is the observational power Balazs and colleagues exploited, not imaging the structure directly, but using the GRBs as luminous markers placed by nature at cosmological distances, each one a beacon illuminating a galaxy otherwise hidden behind the veil of cosmic distance. The primary detection instrument used to compile the GRB catalog for this analysis was the SWIFT Gamma-Ray Burst mission, a NASA satellite launched on November 20, 2004, into a low Earth orbit at approximately 600 kilometers altitude. SWIFT carries 3 science instruments. The Burst Alert Telescope monitors a wide field of view of approximately 1.4 steradians, roughly 11% of the full sky at any given time, in hard X-rays between 15 and 150 keV, looking for the rapid flux increases that signal a gamma-ray burst. When a burst is detected, SWIFT autonomously slews to point its 2 narrow-field instruments, the X-ray telescope and the UV optical telescope, at the burst position within about 90 seconds of the initial detection. The X-ray telescope operates between 0.3 and 10 keV and measures the rapidly fading X-ray afterglow, providing an arc-second precision localization that can be distributed to ground-based telescopes within minutes via the gamma-ray burst coordinates network. Ground-based observatories can then obtain optical and near-infrared spectra of the afterglow, from which the redshift is measured. The entire pipeline, from detection to redshift measurement, can operate in as little as a few hours for a bright afterglow at a well-placed location on the sky. The Fermi Gamma-Ray Space Telescope, launched in June 2008, provides complementary gamma-ray detections at higher energies. Fermi's gamma-ray burst monitor covers the entire unoccultant sky at energies from 8 keV to 40 MeV, providing the broadest energy coverage of any current space-based gamma-ray detector and detecting approximately 250 bursts per year. Fermi's Large Area Telescope, operating at energies above 100 MeV, provides high-energy detections for the most powerful bursts.
The combination of Swift and Fermi, supplemented by older data from BATSI aboard the Compton Gamma Ray Observatory and missions like BEPOSAX, HETE2, and Integral, provided the input catalog from which the 19 GRBs used in the Hercules Corona Borealis Great Wall analysis were drawn. Building a catalog of redshift-measured gamma-ray bursts at a specific epoch of cosmic history is not a quick endeavor. Gamma-ray bursts occur at a rate of roughly 1 per day detectable by Swift anywhere in the sky. Of those, not all are followed up spectroscopically. Some occur during the day at the longitudes of the major optical observatories, some are obscured by the galactic plane, some fade too rapidly before a spectroscopic telescope can be retargeted. Of those with redshifts measured, only a fraction fall in any specific redshift window of interest. The 19 GRBs in the Z equals 1.6 to 2.1 range used by the Budapest team represent the accumulation of more than a decade of observations drawn from a total archive of several GRBs with measured redshifts. Each data point in the analysis is the product of a chain of events: a stellar death billions of light years away, a burst of gamma radiation concentrated into a jet aimed by chance toward Earth, a detection by an orbiting satellite, an autonomous spacecraft maneuver, a robotic alert to ground-based observatories, a spectroscopic observation on a dark night at a telescope in Chile or Hawaii or the Canary Islands, a manual analysis of the resulting spectrum, a published redshift. Each of those chains for each of the 19 bursts had to succeed. The data was assembled one explosion at a time across more than a decade in the patient and cumulative manner that characterizes the best of observational astrophysics.
To understand the full weight of what the Budapest team found, we need to begin where they began, with what the standard cosmological model predicted they would find. The lambda CDM model, the standard model of cosmology, where lambda represents the cosmological constant corresponding to dark energy and CDM stands for cold dark matter, is the most precisely tested physical model ever constructed by human science at cosmological scales. Its parameters have been constrained by multiple independent lines of evidence to an accuracy that would have been unimaginable 50 years ago. The composition it describes, approximately 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary baryonic matter, has been independently confirmed by the cosmic microwave background power spectrum measured by the Wilkinson Microwave Anisotropy Probe and the Planck satellite, by the distance redshift relation of Type 1a supernovae, by the Big Bang nucleosynthesis predictions for the abundance of light elements, and by the large-scale clustering of galaxies in surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. Each of these measurements, conducted with different instruments using different physics, converges on the same parameter set. This convergence is what gives lambda CDM its authority. Within lambda CDM, the large-scale structure of the universe grows from an initial distribution of density fluctuations that are nearly but not perfectly uniform. These fluctuations originated as quantum mechanical noise in the energy field that drove cosmic inflation, the period of exponential expansion in the first tiny fraction of a second after the Big Bang, during which the universe grew from a volume smaller than a proton to roughly the size of a grapefruit in approximately 10 to the power of minus 32 seconds. Inflation stretched those quantum fluctuations to macroscopic scales and imprinted them on the energy density of the universe as minute variations of 1 part in 100,000 in the temperature of the early plasma. When the universe cooled enough for matter to become neutral at about 380,000 years after the Big Bang, those temperature variations became density variations. High-density regions, even by a few parts in 100,000 above average, began to gravitationally attract more matter. Over hundreds of millions of years, they collapsed into the first stars and galaxies.
Over billions of years, gravity amplified these seeds into galaxy clusters, then into the filamentary cosmic web we observe today. Lambda CDM makes a specific testable prediction about the statistical properties of this web, the matter power spectrum. The power spectrum describes, as a function of spatial scale, how much variation in matter density to expect. At small scales, the scale of galaxies and galaxy clusters, there is lots of power, huge variations in density from one region to the next. At large scales, the power declines. At the homogeneity scale of roughly 1.7 billion light-years, the power has dropped to a level where statistical variations in density from one region to another become negligible. Beyond that scale, lambda CDM predicts an essentially featureless distribution, no coherent structures, no overdensities that span billions of light-years, nothing that looks like a wall or a ring or a filament. This prediction is extremely robust to small changes in the model parameters. You can vary the Hubble constant, or the dark matter fraction, or the spectral index of the primordial power spectrum within the ranges allowed by current observations, and the homogeneity scale changes by at most a factor of a few. You cannot, within any currently acceptable variation of lambda CDM, produce a coherent structure at 9.7 billion light-years. In January 2015, Borealis and colleagues published their analysis in the monthly notices of the Royal Astronomical Society. The paper, titled "A Giant Ring-like Structure at 0.78 less than Z less than 0.86 by Gamma-ray bursts," though note this was a distinct earlier finding about a ring. The Great Wall paper was published simultaneously, addressing the Hercules corona borealis feature, documented their methodology with considerable care. For the Hercules corona borealis structure, the sample consisted of 19 long gamma-ray bursts with measured spectroscopic redshifts between Z equals 1.6 and Z equals 2.1, drawn from the Swift BAT archive, supplemented by Fermi and BATC detections. The bursts were selected purely on the basis of having measured redshifts within the target window, with no prior knowledge of their angular positions, an important control against selection bias. The 2-point angular correlation function was calculated for the 19-burst sample. This function measures, for every pair of bursts, whether they are more closely associated in angular position than a random distribution would predict. It is a standard tool in large-scale structure studies. A positive correlation signal at some angular scale means bursts are clustering at that scale. The signal found in the Hercules corona borealis sample was a clustering excess at an angular scale of approximately 40 to 50 degrees, with a statistical significance measured against 100,000 Monte Carlo simulations of randomly distributed catalogs with the same angular coverage as the real data, of approximately 0.07% chance of arising by random fluctuation. That is a 3.3 sigma detection in Gaussian statistics. It corresponds to roughly a 1 in 1,400 probability of being a statistical fluke. Let us make the discrepancy concrete with an analogy. Imagine that you are a quality control inspector at a factory that produces dice. The specification is that every die should be perfectly unbiased. Each face should come up with probability 1 in 6. You test a die by rolling it 19 times and recording the results. If the die is fair, you expect a roughly uniform distribution of faces with some statistical scatter. Now suppose all 19 rolls come up the same number. The probability of that happening with a fair die is 1 in 6 to the 18th power, vanishingly small, and you would immediately conclude the die is weighted. The Hercules corona borealis case is not quite that extreme, but it is analogous in structure. The gamma-ray bursts are distributed in a way that, if the universe is fair, that is, homogeneous above the 1.7 billion light-year scale, should occur in fewer than 1 in every 1,000 random realizations of the same observational setup. The die appears to be weighted. The question is, by what?
Within lambda CDM, the large-scale structure of the universe grows from an initial distribution of density fluctuations that are nearly but not perfectly uniform. These fluctuations originated as quantum mechanical noise in the energy field that drove cosmic inflation, the period of exponential expansion in the first tiny fraction of a second after the Big Bang, during which the universe grew from a volume smaller than a proton to roughly the size of a grapefruit in approximately 10 to the power of minus 32 seconds. Inflation stretched those quantum fluctuations to macroscopic scales and imprinted them on the energy density of the universe as minute variations of 1 part in 100,000 in the temperature of the early plasma. When the universe cooled enough for matter to become neutral at about 380,000 years after the Big Bang, those temperature variations became density variations. High-density regions, even by a few parts in 100,000 above average, began to gravitationally attract more matter. Over hundreds of millions of years, they collapsed into the first stars and galaxies. Over billions of years, gravity amplified these seeds into galaxy clusters, then into the filamentary cosmic web we observe today. Lambda CDM makes a specific, testable prediction about the statistical properties of this web, the matter power spectrum. The power spectrum describes, as a function of spatial scale, how much variation in matter density to expect. At small scales, the scale of galaxies and galaxy clusters, there is lots of power, huge variations in density from one region to the next. At large scales, the power declines. At the homogeneity scale of roughly 1.7 billion light-years, the power has dropped to a level where statistical variations in density from one region to another become negligible. Beyond that scale, lambda CDM predicts an essentially featureless distribution, no coherent structures, no overdensities that span billions of light-years, nothing that looks like a wall or a ring or a filament. This prediction is extremely robust to small changes in the model parameters. You can vary the Hubble constant, or the dark matter fraction, or the spectral index of the primordial power spectrum within the ranges allowed by current observations, and the homogeneity scale changes by at most a factor of a few. You cannot, within any currently acceptable variation of lambda CDM, produce a coherent structure at 9.7 billion light-years. In January 2015, Ballas and colleagues published their analysis in the monthly notices of the Royal Astronomical Society. The paper, titled "A Giant Ring-like Structure at 0.78 less than Z less than 0.86 by Gamma-ray Bursts," though note this was a distinct earlier finding about a ring, the Great Wall paper was published simultaneously addressing the Hercules corona borealis feature, documented their methodology with considerable care. For the Hercules corona borealis structure, the sample consisted of 19 long gamma-ray bursts with measured spectroscopic redshifts between Z equals 1.6 and Z equals 2.1, drawn from the Swift BAT archive supplemented by Fermi and BAT-C detections. The bursts were selected purely on the basis of having measured redshifts within the target window, with no prior knowledge of their angular positions, an important control against selection bias. The 2-point angular correlation function was calculated for the 19-burst sample. This function measures for every pair of bursts whether they are more closely associated in angular position than a random distribution would predict. It is a standard tool in large-scale structure studies. A positive correlation signal at some angular scale means bursts are clustering at that scale. The signal found in the Hercules corona borealis sample was a clustering excess at an angular scale of approximately 40 to 50 degrees, with a statistical significance measured against 100,000 Monte Carlo simulations of randomly distributed catalogs with the same angular coverage as the real data, of approximately 0.07% chance of arising by random fluctuation. That is a 3.3 sigma detection in Gaussian statistics.
It corresponds to roughly a 1 in 1400 probability of being a statistical fluke. Let us make the discrepancy concrete with an analogy. Imagine that you are a quality control inspector at a factory that produces dice. The specification is that every die should be perfectly unbiased. Each face should come up with probability 1 in 6. You test a die by rolling it 19 times and recording the results. If the die is fair, you expect a roughly uniform distribution of faces, with some statistical scatter. Now suppose all 19 rolls come up the same number. The probability of that happening with a fair die is 1 in 6 to the 18th power, vanishingly small, and you would immediately conclude the die is weighted. The Hercules Corona Borealis case is not quite that extreme, but it is analogous in structure. The GRBs are distributed in a way that, if the universe is fair, that is, homogeneous above the 1.7 billion light-year scale, should occur in fewer than 1 in every 1,000 random realizations of the same observational setup. The die appears to be weighted. The question is, by what? The first and most immediate counterargument is sampling bias in the GRB detection and follow-up process. Gamma-ray bursts are not detected uniformly across the sky. Swift has a particular pointing history. It cannot observe the sun or moon and must avoid certain bright X-ray sources, and the distribution of burst detections reflects that history. Ground-based spectroscopic follow-up is further biased by the locations of major telescopes, which are concentrated in the northern hemisphere and in a few southern sites, and by the competitive allocation of telescope time, which may preferentially favor bursts in certain parts of the sky or at certain times of year. If the 19 GRBs in the Hercules Corona Borealis sample happened to cluster in a region of sky that was preferentially observed, their apparent angular clustering could reflect observational bias rather than physical structure. The Budapest team addressed this directly. Their Monte Carlo simulations were not simple random distributions on a sphere. They were random distributions with the same angular coverage function as the real data, meaning that regions of sky that were more thoroughly observed in the real catalog were also more heavily sampled in the random simulations. The clustering signal in the real data was evaluated against simulations that incorporated the same observational biases. The signal survived. This is the appropriate analysis. It does not completely rule out selection effects. There are forms of observational bias subtle enough to evade this correction, but it represents a rigorous treatment of the known biases in the data. The second counterargument is line-of-sight projection. Even with redshifts measured, the 19 bursts span a window of z equals 1.6 to 2.1 in redshift, which corresponds to a physical depth of roughly 1.7 billion light-years along the line of sight. Within that depth, could some of the bursts be physically unrelated, appearing only to cluster on the sky because they happen to project onto similar angular positions from Earth? This concern is mitigated by the redshift window design. 1.7 billion light-years of depth is large enough to contain genuine physical structures. Actually, it is the homogeneity scale itself, but it is small enough that bursts within it are plausibly within the same large-scale structure. The redshift measurements themselves, being individually precise to within a few percent, confirm that the bursts are genuinely at similar distances. A pure projection artifact would require coincidental angular alignment of bursts at very different distances, which becomes increasingly implausible as the number of such coincidences required grows. The third and more substantive objection is that gamma-ray bursts may not be unbiased tracers of the matter distribution. Long gamma-ray bursts require the deaths of massive stars, and massive stars form preferentially in environments with high star formation rates, specifically in gas-rich, metal-poor galaxies and in the most actively star-forming regions within galaxies. the cosmic star formation rate history peaks at a redshift of approximately 2, which is within the window studied here, meaning that the epoch of the Hercules Corona Borealis structure corresponds to the peak of star formation activity in the universe. If the spatial distribution of star formation at z equals 1.6 to 2.1 is itself non-uniform, clustered into dense regions that trace the underlying matter distribution more strongly than, say, the general galaxy population, then the GRB distribution might overstate the degree of matter clustering. This is the strongest version of the objection, and it cannot be fully dismissed with current data. However, the scale of the effect needed to produce the observed signal from GRB bias alone is extreme. Known correlations between the gamma-ray burst rate and the properties of host galaxies introduce clustering at the scale of galaxy clusters and perhaps galaxy filaments, at most a few 100 million light-years. To produce apparent clustering at 9 to 10 billion light-years through GRB bias alone would require the star formation rate at that epoch to be dramatically enhanced over a coherent volume far exceeding any known structure. The physics of star formation does not support that scenario. The bias objection does not go away, but it also does not explain the observation. The most serious limitation of the current analysis is statistical. 19 GRBs is a very small sample from which to make a claim of this magnitude. In a sample this small, a single misassigned redshift, a burst whose redshift is incorrect due to, say, a skyline contamination of the spectrum or an incorrect identification of an emission line, could meaningfully alter the angular clustering signal. And even without errors, small samples are subject to significant Poisson noise. In any random distribution of 19 points, there will be some clustering, and distinguishing real clustering from Poisson fluctuation at 3.3 sigma requires careful statistical treatment. The analysis performed by the Budapest team was rigorous, but it is not the final word. The final word will require a sample of hundreds of GRBs at the same redshift, drawn from a uniformly observed sky survey with consistent spectroscopic follow-up. That dataset does not yet exist. What persists through all of these caveats is the core tension. The signal is real in the data available, it exceeds what random distributions of GRBs with the same sky coverage produce, and it implies a structure, if real, that is incompatible with standard LCDM. The Hercules Corona Borealis Great Wall is not merely a record, it is a discrepancy. And discrepancies of this magnitude in well-analyzed astrophysical data historically do one of two things: they go away with more data, or they change the underlying theory. We do not yet know which of those paths this anomaly will follow. That resolution is pending, and the pending nature of that resolution is itself significant. There is a broader context for this anomaly that is worth acknowledging. In the years since the Hercules Corona Borealis Great Wall was announced, several other large structures have been identified at or beyond the homogeneity limit. The huge Large Quasar Group, announced in 2013, comprises 73 quasars spanning approximately 4 billion light-years, more than twice the homogeneity limit, with a statistical significance of roughly 4 sigma above random expectation. The Saraswati supercluster, identified in 2017 by Indian astronomers and published in the Astrophysical Journal, spans approximately 1.3 billion light-years and is notable for its enormous mass, about 20 million billion solar masses. The South Pole Wall, discovered in 2020 using peculiar velocity surveys that map the motions of
galaxies rather than their redshifts, stretches for approximately 1.37 billion light-years and sits precisely at the theoretical homogeneity limit. None of these individually constitutes a decisive challenge to the cosmological principle, but taken together with the Hercules Corona Borealis Great Wall, they suggest that the universe may be systematically more structured at large scales than lambda CDM predicts. The question is whether this is a statistical accident, the tale of an otherwise well-behaved distribution, or a sign that the distribution itself is not what we think it is. Step back now from the specific data and the specific statistical tests and consider what is at stake at the level of fundamental cosmological theory. The cosmological principle, the assumption of large-scale homogeneity and isotropy, is not a hypothesis that was formulated and then tested. It is an assumption that was built into the foundational framework of cosmology before the observational tools to test it properly existed. Einstein applied it in 1917 because it made the mathematics tractable. Friedman, Lamette, Robertson, and Walker used it in the 1920s and 1930s to derive the equations of cosmic expansion. By the time observational cosmology had matured enough to test it, which required galaxy surveys of sufficient depth and sky coverage that did not become available until the 1990s and 2000s, the cosmological principle had been embedded so deeply in the theoretical structure that questioning it felt radical. The current observational status is nuanced. Most large-scale structure surveys are consistent with homogeneity at and above the homogeneity scale within their statistical uncertainties. The cosmic microwave background is isotropic to 1 part in 100,000, one of the most precise confirmations of any cosmological prediction ever made. Galaxy redshift surveys at moderate depths show clear convergence toward homogeneity as the volume considered grows. The standard model is not obviously wrong, but the existence of apparently super-horizon structures, structures larger than what the theory allows, introduces a tension that cannot be simply dismissed. Either the structures are real and the theory needs revision, or the structures are not real and the data needs better analysis. Both possibilities require more work, more data, and more theoretical creativity than the current situation provides. If we take seriously the possibility that the Hercules Borealis Great Wall and similar structures represent genuine violations of the homogeneity limit, what theoretical modifications might accommodate them? The most conservative possibility involves a revision of the initial conditions, specifically the spectrum of primordial density fluctuations produced by inflation. Standard slow-roll inflation predicts a nearly scale-invariant spectrum, but nearly is not exactly, and observational downs on deviations from scale invariance still leave room for enhanced power at specific scales. If the primordial spectrum had an excess of power at very large scales, corresponding to length scales of several billion light-years today, gravity could have amplified those excess fluctuations into structures larger than what the standard spectrum predicts. This is a small modification to inflationary theory, not an abandonment of it, and it is testable in principle. It would leave a specific signature in the angular power spectrum of the cosmic microwave background at the lowest multiples, the largest angular scales in the CMB, as measured by WMAP and Planck, where current measurements already show some unexplained features. The quadrupole anomaly and the octopole alignment, departures from statistical isotropy at the largest angular scales in the CMB as measured by WMAP and Planck, have been discussed in the context of possible modifications to the primordial power spectrum, though these too remain contested. A more radical set of possibilities involves actual violations of isotropy or homogeneity as global properties of the universe. Some theoretical frameworks postulate a universe that is not simply lumpy, but fundamentally anisotropic, with a preferred direction set by, for example, a large-scale magnetic field threading the early universe, or a topological property of the cosmic manifold that creates patterns at very large scales. Others invoke what are sometimes called void models, in which the universe is actually inhomogeneous at large scales, with the Earth located in an unusually underdense region that mimics the effects of dark energy through local gravitational dynamics rather than through a global cosmological constant.
These models have largely been ruled out by independent observations that constrain the large-scale velocity field of galaxies, but they represent the kinds of creative theoretical proposals that anomalies like the Hercules Corona Borealis Great Wall motivate. The deepest possibility, and the one that is most genuinely troubling from a theoretical standpoint, is that the structure reflects something about the pre-inflationary universe that survived inflation. Standard inflation is designed to erase large-scale features. The exponential expansion takes any structure that existed before inflation and stretches it to scales far beyond the observable horizon, rendering it unobservable. This is inflation's great virtue from a cosmological perspective. It solves the horizon problem, the fact that the cosmic microwave background is uniform to 1 part in 100,000, even across regions that were never in causal contact in the pre-inflationary universe, by positing that all of the observable universe was in causal contact before inflation began and then was exponentially expanded. But if inflation was not precisely the standard slow-roll variety, if it had a non-trivial structure, or if it ended differently in different regions of the pre-inflationary volume, it might have imprinted features on the post-inflationary universe at scales that we can observe. The Hercules Corona Borealis Great Wall would then, in that case, be a relic of the state of the universe before our observable cosmos began. That would be extraordinary. It would mean we have found a window into a period of cosmic history that inflation was supposed to make forever invisible. Set aside for a moment the specific uncertainty around the Hercules Corona Borealis Great Wall and pull back to the largest possible perspective. We exist at a particular moment in the history of the universe, approximately 13.8 billion years after the Big Bang, and from this moment we have access to a particular finite volume of space bounded by our particle horizon at roughly 46 billion light-years in co-moving distance. Within that volume, we can observe the cosmic microwave background, the large-scale structure of galaxies, the spectra of distant quasars, the afterglows of gamma-ray bursts. We have built, from these observations, a model of cosmic history that is precise to within 1% or 2% on the key parameters, and that agrees with multiple independent data sets. This is a genuine intellectual achievement, one of the great accomplishments of 20th and 21st century science. But this model sits on top of an assumption, the cosmological principle, whose testability is fundamentally limited by our location in space and time. We cannot observe the universe from another location to check whether it looks different. We cannot wait long enough to see what the universe looks like from a different temporal vantage point. We are, in a real sense, stuck at a single observational platform, looking outward in all directions from one point in a 93 billion light-year sphere, trying to infer the properties of a universe that may extend beyond our observable horizon for an immensely larger volume, perhaps infinitely so. Everything we know about cosmology is derived from what is visible from this one platform, and the question of whether what is visible from this platform is representative of the whole is, at a fundamental level, unanswerable from this platform. The expansion of the universe, driven by dark energy, which constitutes approximately 68% of the total energy density, is accelerating. Space between gravitationally unbound objects is growing faster every year. Galaxies beyond our local group are already receding from us at speeds that exceed the speed of light in cosmological terms, not because they are moving through space faster than light, which is forbidden by special relativity, but because the space between us and them is stretching faster than light can cross it. That light it emits today is moving toward us at 300,000 kilometers per second, but the space it must traverse is growing faster than it can cover. That light will never arrive. Those galaxies are already, in a precise physical sense, beyond our cosmological event horizon, even though they appear in our current sky because the light we see from them left long ago when they were close enough for their light to make the crossing. As time passes, more and more galaxies will cross beyond our event horizon. In roughly 150 billion years, about 10 times the current age of the universe, every galaxy outside the local group will have receded past the point of no return. Their light, even their most recently emitted light, will never complete the journey to us. The observable sky, viewed from the merged Milky Way Andromeda galaxy, the object astronomers call Milkomeda, will contain only those galaxies gravitationally bound to the local group, perhaps 50 or 60 dwarf galaxies surrounding a single large elliptical embedded in empty darkness extending in all directions to infinity. Any civilization that exists at that epoch and attempts to do cosmology from within Milkomeda will observe a static, isolated galaxy surrounded by nothing. They will have no evidence for cosmic expansion. They will have no evidence for the Big Bang. The cosmic microwave background, the afterglow of the hot early universe, will have been redshifted to a temperature indistinguishable from absolute zero, its photons stretched to wavelengths far larger than any antenna they could build. The entire observational basis for modern cosmology will have been erased by the passage of time and the relentless expansion of space. They will be wrong about the universe, and they will have no way to know it. This is not a hypothetical future problem. It is a mathematical certainty as robust as any prediction in physics. We, living now, are in possession of cosmological information that will be permanently unavailable to all future civilizations. The cosmic microwave background, visible to us across the entire sky, a fossil of the first 380,000 years of cosmic history, will be gone. The distant galaxies that allow us to measure the expansion rate and confirm the existence of dark energy, gone. The gamma-ray bursts that trace the large-scale structure at cosmological redshifts, their host galaxies gone beyond the horizon, their afterglows too faint and too redshifted to detect. The information we use to build our cosmological model is a resource that is being depleted with every passing billion years as more of the universe crosses beyond our observable reach. We are, in a very real sense, living in the observational golden age of cosmology, the brief window between when the universe was too hot and ionized to be transparent and when it will be too expanded to be visible. What the Hercules Corona Borealis Great Wall represents in this context is an anomaly at the edge of our current understanding, a feature in the data that either requires us to revise our models or, with more data, will dissolve into the statistical background. Either outcome will tell us something important. If it dissolves, we will have learned that small samples at cosmological distances produce misleading statistics patterns, and we will design better surveys accordingly. If it persists and is confirmed, we will have learned that the universe at large scales is not as smooth as we assumed, and we will need to revisit the foundational principle on which our models rest. That revision would not destroy the standard model, it would constrain and refine it in ways we cannot yet anticipate. Science doesn't work by building perfect theories that never need revision. It works by building the best theories available with the best data available, and then letting anomalies in the data tell us where the theories need to grow. The Hercules Corona Borealis Great Wall is an anomaly, and anomalies in the history of physics have a way of being important. What we're left with, after the data, after the statistics, after the theoretical implications and the cosmological framework and the far future fate of the observable universe, is the simple fact that the largest known structure in the universe does not fit comfortably inside the universe as we understand it. Whether that turns out to be a problem with the structure or a problem with our understanding is a question that more and better data will answer. We exist right now in the one narrow window of cosmic history when that question is even answerable. If you found this video worth your time, do not forget to leave a like and subscribe. It makes a genuine difference for the channel and helps this kind of content reach the people who are looking for it.